Well, hello everybody. Today we are continuing with our small toy programming language. Um, as usual, if you have any questions, put them in the chat in Zoom, and um, I will I will be monitoring it, and I will answer any questions you might have. Last time we talked about the lexer, which is a part of our interpreter that deals with low-level terminal parts of our grammar. And today we are going to be looking at the parser, but we won't look at the parser in its entirety. We'll just look at expressions because this is a good place to start, and you will always, in every context in your program, deal with expressions. So that's what we are going to be dealing with. Okay, so let's move on. Here's our favorite expression, which I've been dragging around for some time now. So in order to, first I need to clarify what the parser kind of is supposed to do and what its purpose in life, in theory and formally. So if we take some input and we have a parser for some grammar, and we feed this input into that parser, what we are supposed to kind of get is verify. So the parser is going to tell us, does this input comply with the grammar or does it not? So that's the initial kind of purpose, I guess, of parsing. So we just check whether or not some given text belongs to some given language or kind of fits into the grammar. But actually, it's not, well, it's boring, right? Why do we need to, if we write in a language, why do we need to check if we have written something in that language, right? So for our purposes, the parser, it will still answer this same question, but it will answer it in well, in a weird way, I guess. So if the input is okay in terms of grammar, we will get a successful parsing result in the form of an AST or abstract syntax tree. And if it's not, well, we will still get an AST, but it will be invalidated. So it will be marked as an error. So we get some result in either case, but in terms of an invalid or malformed program, we will get something out. But we will look at errors a bit later. And today we are not concerned about them. So today we are looking at expressions specifically, and we assume that any input is correct always. Okay, so our expression here, this is a binary additive expression, and it will look like that in an AST. So it will boil down to some parts which are organized in a hierarchy, and they reflect some grammatic production in our grammar. As for AST, though, today we are not going to be building it. I will show you the places where it will be created, but AST Builder and an AST printer is something we will be looking at next time. Today is just parsing expressions. Okay, so to remind us the grammar, what we have a program which will be consistent of a single expression. And when we say expression, we actually mean an additive expression plus or minus, a binary plus or minus. And additive expression can have multiplicative expressions as its operands, which are multiply or divide. And the grammar is structured in such a way that the operation precedence is baked into the grammar. So we cannot build the tree in any different way. And I will show you how it will work when we get to the code today. Also, the multiplicative expression, its operands are unaries. And a unary expression is defined in terms of a primary expression. So it's a unary operator. It can be plus or minus, and it is followed by another unary expression, and this continues until we just run out of operators. So if you look at this grammar for unary in the top right corner, it's defined as a primary or unary operator and unary expression next. So we either get a literal or an open paren right away, or we get plus or minus, and in which case we consume this plus or minus and go to unary again. So we'll look at how it works. And this allows us to write things like minus, 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 minus 2. Paren expression is, of course, an expression in parentheses, and a literal expression is our number. But in our case today, well, it doesn't make any difference really, but it's not just a number. In our case today, it's going to be an int, a float, or true or false, because those things our lexer already understands. So we'll just leave them there, even though we won't be dealing with any real calculations or Boolean logic or whatever. Okay, and to parse this grammar, we are going to be implementing by hand the recursive descent method. So we are going to have a recursive descent parser, because that's the only thing you can reasonably write by hand. So why is it recursive and why is it descent? Right? Those words are related kind of to the grammar, not to anything you get as input. So I don't know, when I first heard about this recursive descent parsing, I was like, like, what do you mean descent? And other parser types, like an ascending parser. How do you ascend the code? Oh, no, it doesn't. It has nothing to do with code. It has everything to do with the grammar. So descent means that we enter from the root kind of the grammar. In our case, it's program. And this red dot before 42 it kind of symbolizes where in terms of the input on which token we are now kind of parked. So we go into the program. Our grammar says that our program is expression. So our parser, when we enter this program thing, we go and enter the expression rule and see what it is. And then we enter the additive expression, which in turn then, since its operands are multiplicative expressions, it will try to figure out its left operand, and it will go into the multiplicative expression production and see if it's, well, if that's fine. And then the multiplicative in its turn will call unary and will call primary, and eventually we will descend all the way down to the literal rule of production, and in which case we will consume it and move to the next token. Well, not necessarily token, but we will consume this part which matches our kind of small brick, and we will move on to the further. Okay, so at this case, we have consumed kind of 42, and we roll all the way back until some criteria are met. So in our case, we see a plus here, and we will be going back the call tree until we get back to the additive expression, because we have a plus, and this is what additive expression is looking for after its left operand. And at this point, we will have consumed the literal, and we will have an AST node which reflects this 42 literal. Okay, next, since we have a plus here, that's an additive expression, so we will continue within the additive expression. And then, after plus, when we move past the operator, we will repeat this entire process of descent into the grammar again. We will reach the literal again, and we will have like a second operand. And on the way back, in when we reach again to the additive expression production, we will combine those into this structure, into the binary. Well, if we look back at the grammar, which we are going to do momentarily, okay? So it's, we are going to the code. If we look at the grammar, we have a whole bunch of binary expressions here. Like we have logical OR, we have logical AND, quality, which is equals operator, additive, multiplicative, and so on. We are going to be looking today at this subset. Addition, multiplication, unaries. This postfix thing will never come up because we don't have functions yet. And then a primary expression, and everything more terminal than that, so to speak. And here's where it gets recursive, because we start the program with an expression, and during our descent, we can kind of recurse back into production rules which are higher than we are currently in the kind of this grammar hierarchy. Okay, and I have this file here, which is what we eventually will be able to do. But what I'm going to do is just go and type our thing here and disregard everything below, because this is what we are going to be dealing with. And I'll go ahead and, well, break the parser I already have quite a bit, and I will kind of dumb it down so we can a better look what's going on first. We will get back to the normal thing, like in subsequent sessions like that. Okay, so what we are going to be doing here is we are going to load this file I have here, into a string. And we are going to feed this string to a parser. Also, I have to mention, we have those two things here, Sema and builder. Builder is something we will look at next time. And Sema is a semantic analyzer, which we'll be dealing with a little bit later when we get to defining our own names in programs, basically. Variables, functions, and we also it's going to be related to types. But today we are not going to worry about that. Okay, so how do I break my parser and make it more compliant with our goals? So, well, first, I will go ahead and define those guys here. Since we are looking at an additive and multiplicative, we will have additive and multiplicative today. And you might ask, like, oh, wait a second, why didn't you have them, right? Where were these additive and multiplicative expressions? And that's because we have this binary expression thing, and I will explain it after we look at the stupid version of the parser, and then we are going to make it a little bit smarter. Okay. And let me see, put them here. So that's our additive, that's our multiplicative expression. And our program, which I literally have this a thing called program, like the function of the parser. Instead of doing this list thing, which we will also be looking at, I'll just call export. And export will also call just add export, because we don't have variables yet. All right, so how do we write this? Oh, by the way, I should also do something which will help us, which I would never recommend doing in any kind of production code. But our parser is now dependent on iostream temporarily. All right, so how do we write this add export thing? Well, our grammar, if we look at the grammar, what does it say about this additive export? It says multiplicative export or additive export addition operator multiplicative export. And this, I think I discussed this when we were looking at the grammar. This is left recursion. So additive export is defined in terms of an additive export. And it's bad. If you do it like in a straightforward, I should call it probably dumb way, like if you're just calling functions named as the grammar functions. But since we know that an additive export is defined in terms of a multiplicative export, we can use that. as well. Instead of this, we can use a multiplicative export and then check for the operator, and kind of we are unwrapping the grammar in our code, and we are avoiding recursion infinitely in this case. Okay, by the way, the parser, its structure is really simple. If we just take a look at the parser itself and compare it to what we have in the grammar, you will see that program, declaration, decl this, decl that, statements, expressions, and so on. So the parser, it just has functions inside of it, which repeat the structure of grammar. Like every non-terminal symbol, for the most part, we will have a function for it inside the parser. And the parser owns a lexer, and when you feed input into it, into the parser, it will feed this input into lexer, and it will come, it will start going and start like parsing the things according to the grammar. Okay. This operator is used to seed it with input. So, okay, back on track. Oh, how can we write this add export function? Well, we know that the left operand of an additive expression is a multiplicative expression. If we look under this, if we unwrap this grammar, kind of, we will go manually in our head. We will go inside this, inside this additive expression, go and go and go until we reach this multiplicative expression, and we'll say, hey, this is what we are going to call. So we call the multiplicative expression. And now something will happen. So the parser will dig down into the grammar. It will create something eventually. It will reach a literal or whatever. And we will eventually go back. And now we will have this operator, plus or minus, in front of us. Or if we did not write, like if we'd go ahead here, and we'll just go like that, right? Or even like that. This is a valid expression, and just 42. If we do that, we will not have an operator in front of us, in which case we are done with the additive expression and we can move back. Okay, so if we go on our reflex kind of, we would say, well, what are we going to do with this operator? We'll just consume it, right? If it's something we're looking for, and go ahead and kind of continue indefinitely. But we cannot really do that. We cannot just go ahead and consume the operator and call it day, because our expressions can be complex. So let's say we have this, I don't know, I'm out of digits and numbers. If we have this, okay, that's okay, right? But what if those things were pluses? So if we go here, say, oh, hey, it's a plus, let's consume it. Oh, hey, let's go produce the right operand of our additive expression, and oh, okay, we are done. We will parse the whole thing incorrectly, right? And also, we have to remember here that the arithmetic operations like addition, multiplication, and so on, they are left associative. I think I touched upon this, but I will touch upon this again. So if you have that, in the resulting tree, you will have like plus 22 and 10. If you have that, what are you going to have in the result? This part becomes the left operand of the entire expression. And this part becomes the right operand of the entire expression. So we need to respect that also. So you will have that. So it's a binary operation which has as the left operand a binary operation, and as the right operand it has like a literal. And this is always true for arithmetic expressions which have repeatedly in the same expression the operator of the same precedence. So it's very, very easy to do it in reverse, you know, like that. I think I did it before, so I used to do it once when I was trying to figure out first how to do that. And if we did that, for plus, it's not going to be a big deal, but if we do minus here, we will get different results in the end. So this associativity thing, it's really, really important. And in order to do this kind of thing properly, what we have to do is do it in a loop, basically. So we'll say while good, this is our left operand of our hypothetical additional expression at this stage. And we'll have a peek into the next token. Let's go behind. Oh, that's B. And remember, lexer peek, what it does, the lexer has a little optional inside of it, and it fills it with a preview token, so it previews the next token without moving anything. So it will, if the optional inside the lexer is empty, it will create a token there, and no matter how many times we call peek after that, it will just give us the same thing. So peek, mean, right? And this is the token we think is the operator. And we have to check whether or not it's the operator in reality. So what we have to do here is check that it's not equal to a plus, and it's not equal to a minus. And if it's none of these things, we'll just bail out. So we're done here. If it is, what we are going to do is consume it. So we'll just tell the lexer, okay, give us this token it's ours now. And the next time after we call next, the next time we call peak, the lexer will process the next token. And here, what? We just copy paste it because why not? You didn't see that. Not yet. So okay. And okay, so where we are here, we have consumed the operator. So in our case, it's, in our input, it's going to be this plus operator. So we have consumed it here, and we now need to build the right operand of our additive expression, which is defined as a multiplicative expression again. And then when this loop comes to the end, the entire additive expression which we have built here, it will become the left operand of the next hypothetical additive expression. So on the second iteration, if we have multiple pluses, for example, we get here, we repeat this process, and we will build another expression which will have the previous expression as its left operand. And you don't have to worry about that. Goodness, why is Zoom? Okay. You don't need to worry about that just yet. The builder again and all those things is a topic for the next time. All right, so this loop is going to go for as long as we have an additive operator between operands before, like in front of us. And that's that. That's the a binary expression which has a plus or minus operator. And now we need to move on to this multiplicative expression, right? And how do we do that? Well, we do Control C and Control V. And here, what we can do is, what we have to do is type binary. And here we are going to type also binary. And here, instead of plus and minus, we have asterisk and slash. Boom. So this is where it becomes stupid, right? So if we have just two kinds of expressions, that's kind of okay, two binary operators, groups of operators. That's okay, but if we have like 5 of them, if we have more, in reality you will have more in a real language. In C++, there is like a huge list of all those binary possibilities. So it becomes a huge copy-paste fest if we have if we do this approach by creating a function for every rule. And that answers the question which I asked, is how come you didn't have add expr and mul expr before, right, in the parser? Because we'll take a different approach, which I will show you in a sec. But first, what we need to do is put out something on screen. So what I'm going to do is I'll just slash. We'll just start putting those cout outputs. We will launch this thing and we will look at what we get. So in here, it's just text. What we are going to have here is let's say it's here, and then we'll go value. Okay. Again, what do we have? We'll have unary, which we'll call postfix expression, but postfix expression is for function calls. In our case, it will always just go through because it will not ever today find any function to call. It will go through and call this primary expression. So we are not going to worry about the postfix thing. It won't come up today. But here in unary, what's going on in unary? So our unary expression is defined in terms of postfix or an unary operator and unary expression, followed by unary expression. And this is like literally what it will say in code here. So we'll look at the next token here and we check, is it a potential unary operator, which is plus or minus? Well, if it's not, then we, here, by the way, it's for the future, it's for the evaluator, but it will return this unknown value, this unary op function. It will return this unknown value if it's not a unary operator, basically for everything which is not a unary operator. So if it's not a unary operator, what we are looking at currently, we'll just delegate the decision making to the next level. So we say it's not a unary thing. We'll just call the postfix here and be done with it. So cout. And let's say just unary. So we didn't make a unary expression here, but we'll just say we were in the unary expression. And here we'll go and say that we have a unary and it has this operator. And okay, so what do we have else? What else do we have? We have a primary expression, which is defined in terms of, like, a primary expression in our grammar is either a paren, which means in parentheses, something in parentheses, or it's a literal, which I will have to correct because I did not update this comment, even though the grammar was updated. But for now, let's say it is just that, just paren and a literal. And what we do here is just check. So we have a multiple choice scenario here. So basically what this function, the only thing this function does, it just goes, if this, it means it's that production. If we are looking next at an open parenthesis, it's the parent expression. If we are looking at a literal, it's a literal expression, identifier, and so on. And if nothing of this list is before us, then it must mean some illegal token here. And we'll create an error, but we won't be dealing with errors today, as I said. So let's put the word primary here. In parent again, well, when we get to this parent expression function, we are sure that we have an open parenthesis before us. Because why? Because this primary expression function already checked that for us. So we'll just consume the parenthesis and we'll call expression. This is where the entire recursion thing comes into play, because in parentheses we can have like other binary expressions, unary expressions, what have you. Other parent expressions, we can also have that. This part is for the future. It deals with a missing closing parenthesis. But what we are going to do here is we'll just go and type here. Parent. And of course, we clean up after ourselves and delete the consume the closing parent from the lexer. And the last thing is a literal, which we are going to also. So let's see, we have the literal expression, which just literally will take the token from the lexer and use it to build an AST node. And in our case, it will also report its value, the literal's value. Okay, so we have parent, we have primary, covered, unary, postfix we don't care about today, and multiplicative, additive. Okay, let's try and run that. First. So if we go here and try it, what we will going to see a bunch of weird things, but what we just did here with our parser is we kind of printed the path we took through the grammar. And this is also known as the parse tree. I know it's a tree, but it is. And let's see in what kind of weird way is it a tree. So it's printed here upside down, and it reflects what we did. So we entered the program production of our grammar first, and then we went to the export production. Let me just do that. I guess it will be better. And also let me do that so we can see the input and kind of compare it against what we have here. We went to export, meaning this entire thing, like it's the initial state. We are standing parked before the first token in our program. Then we moved to the additive, and we were able to create a additive expression with a plus there. We went to unary, which wasn't a unary because we just had 42. And we went to the primary expression and to the literal expression. And the same thing for the left operand. So this is the right operand, this is the left. And the way it's printed here, it's kind of upside down because the left operand, we went into first. So our additive went into here first, this one, unary, primary, literal 42. And then it kind of went back and went to the right operand and made this literal, primary, and unary. Also empty because we did not have any unary operator. Let's, I don't know, let's spice it up a bit. And we have here 10 plus minus 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 2 plus 3. I'm out of digit numbers. And we have a big output for this expression because the expression itself is kind of huge. So again, what happens here? We go into program, go to expression, and then we build at some point and we process an additive expression which has a plus in it. And this plus is this one. This is our additive expression. This is our left operand, and this is our right operand. Because, well, here's multiplication. We will, at the point we came to this plus, we've already built this entire part. This has been completely figured out before we went here. Well, unary is for the 3. Our unary was not there, I guess. For like non-unary with no operator, I shouldn't have put it there, but okay. So we went to unary. It wasn't a unary expression. We went to primary and built a literal 3. This is for the right operand. And for the left operand, we have multiplicative expression, which, if we look at what it has at the left, it has a unary minus. Then it came inside this unary minus, so it consumed the minus, went inside, didn't see any operator, so it went like as usual, unary, primary, literal 42. This is the left operand. And for the right operand, this multiplicative expression went unary, again primary, paren, expr. So here's your recursion. It went to this plus binary, and it built us 3 unary expressions in the row. And of course, this is what we have in the parentheses. And like, let's not be stupid for a moment again. Plus, say I do that, right? So if I just do 42 plus 10 plus 2. So what we've got here is again, program, expression, additive. And this plus is this plus again, because left associativity. So this part is the left operand. This is the right operand of our top level binary expression. And I guess here what I want to do, I'm going to spoiler a bit of the next thing we'll look at, but I think it will be more convenient here. I have a printer for what the parser does, and I will show you what it will build for us. So this output kind of in just a list of strings is inconvenient. This is what our path through the parser was. In order which we kind of met those things. So this helps in terms of, well, how did we get there? Oh, okay, so we have somehow descended all the way down to a literal, built it, went back, went through primary, went through unary, and so on. But this is an AST output, which we will, next time I will show you how that is done. So what we have here, let's get out it again. What we have here is a binary expression which has a left operand, a binary expression. This is our 42 plus 10 thing. And this is our 2 thing, this one. So yeah, that's left associativity. That's a tree. When you have a chain of binaries of the same priority, the tree always grows to the left. Okay. Now let's go, since we are spoiling things, right? Why not? Let's go back to our stupid thing. Minus minus 2. Divided by, I don't know, 8. Let's run it and check it out. Well, again, this is not really informative. I just wanted to show you kind of give you the feel of how the parser flows through its call graph, kind of. But if we look at what we have as a result of this expression you see there in the input. So again, this plus is the last plus we have here. And it's an addition between a multiplication expression this one. And it's a multiplication between a multiplication expression 3, and this part is a multiplication between 42 and something in parentheses, which happens to be a binary expression, and it has like a chain of unaries here as its operand. And we have one last thing left, which I would like to cover today. And And I guess I will just delete those IOStream calls at the moment. It won't take long. I guess. Hmm. Yes. Hit the mic. I hope nobody does. It can be irritating. Sorry for that. Okay. So, how do we avoid this monstrosity? Because right here, right now, we have code duplication of the most kind of idiotic proportion, right? So we have a lot of code duplication here, and we don't want that. So let's see how we can avoid that. Well, first of all, away with those. And here we are going to call a binary expression. We also have here. And this is our one single function which will handle all kinds of binary expressions for us from now on. Now, how it works? We have this enum called precedence, which is defined here. So what it does, it defines different kinds of different groups of operations. So additive is plus or minus. Multiplicative, of course, it's multiplication division. Relational is a group where operations like less than equals, greater, and greater equals fall. Equality is like equality comparison, equals or not equals. And we have logical and logical or. And in our grammar here, the priority precedence of operations is defined kind of this way. So unary, of course, is like the bottom. It's a place where we go after we have run out of binaries. But multiplicative expression, the highest precedence. Additive expression goes after a multiplicative. So if we mix pluses and multiplications kind of in one expression, the additive will be the top one and multiplicative expressions will be its operands. This way, when we go and calculate values, they will be calculated first. And so, yeah, they will be traversed kind of first when we traverse the tree, the AST, which is going to happen all tomorrow actually for the printer. But this is going to be one of the last things we do when we create an evaluator to extensive tree traversal. Okay, so just below additives, we have relational expressions and then equality expressions. So if you write 1 plus 2 is less than 3, for example, you will have 1 plus 2, one operand, 3, another operand, and the less than is, and the entire expression is going to be. So next is equality, logical and the last is logical or. this is the binary operation which has the least possible precedence in our grammar. And you see they're defined kind of upside down because, again, they need to be defined in terms of operations with higher precedence, so that those will become their operands. Okay, so yeah, we have all those enum elements. And we have this small little const export array here, which doesn't hopefully take any memory in our program when we run it with const export. And what happens here? We go inside this binary expression function, and this precedence index is set initially to 0, basically. So we start with logical OR. We start from the least precedence possible when we first enter here. And yeah, if this index, which we get as a parameter of this function, if it has reached past the array, past the last element, so this is element number what? Index 0, 1, 2, 3, 4, 5, right? So yeah, if it's kind of out of bounds already, this means that we have traversed the entire, we've reached the bottom, kind of, and we'll go just unary and bail out. And then we increase this index and recursively call the binary expression again. So let me demonstrate how it works. Yes, and much precedence here. This one is, it's basically just a switch case. Let me show you. Basically just the switch case, which checks different token kinds of operators and fits them into our categories. So if I say much precedence like plus here and additive here, it's going to return true. If I say much precedence additive and something like less, it's going to return false. So it's just a switch case here. Okay, now, so what this means, remember when I wrote those add expr and null expr functions, I did also things like that. So I just checked if in add expr, I checked if we have a plus or minus, right, in the this token thing. The same idea, just more kind of generic. Okay. We do next is, of course, we have the same loop as we had before. And what we do next is we just consume the operator if the operator belongs to our current precedence. And we go again, call the binary export, the same function recursively with the next index. So let's see how it works. And I will just show you at, let's go and do 1, 2, 1 plus 2. So start here. 0 means logical OR. So we go and build the left operand of our expression first. So increase this index by 1. Okay. And we repeat that. So it's 2. And by the way, we will continue doing that until it reaches the end here. Okay, so index of 3. What is it now? 3, 4. Yeah, it looks kind of goofy. Okay, so now we are out of this array. And we go to the unary expression. And now we just return because we have reached the leftmost operand possible, kind of. So in this case, it's 1. So our precedence index is now 5. So we are in a multiplicative expression, basically. And we have just built the left operand of our hypothetical possible multiplicative expression. So let's go ahead and check if we can build the rest of it, right? So we take the next token, which is the operator, and it's a plus. And this much precedence thing function, it will return false for us because multiplicative and plus do not match. So we just break and return. And now we are up a recursion step. And we are going to be inside additive. So our index now corresponds to this additive expression thing. And we are, by the way, we are still here before this plus. So when we went into the multiplicative expression and we built the left operand of that, plus did not satisfy our criteria for it being a multiplicative expression. So we went up. And we are now in the additive expression. And we have built the left operand of it already. Okay, so now this token is a plus, and this match precedence thing will return true for us because plus is an additive operator. So it falls into the additive category. So we now consume the operator token, and we are now here before this 2. And we are going to repeat the entire process. So we are going to go into the right operand of that now. And we are going again. Take this index, move to a multiplicative kind of expression because the index is already high enough. So, and it will continue, yes, for the right operand, the same thing. And this next index here, it's like the same for the left operand and for the right operand. Because left and right operands are expressions of the same kind of binaries, always. Okay, so I guess we will just here kind of it's not really interesting to just go through the same functions. The point is, yes, we were able to build a binary expression correctly. And if we go and do 12 multiplied by 3 plus 2 minus 1 multiplied by... If we start it, I won't... since, recursive calls are kind of pain to debug, I won't do that now, but I'll just show you the result. So we've got a binary, which is a minus, and it has, due to, again, left associativity, a plus as its left operand here. And the plus, this binary plus operand addition operation, it has the left operand. As its left operand, it has this multiplication thing, and 2 as its right operand. And the minus as its right operand has another multiplication. So by using those, jumping through those enums techniques, we can remove the need to copy paste the same function over and over and over again, as we would have done if we didn't do that. Because as I initially showed you, those functions for different kinds of binaries, which are all the same. So yeah, that's that. You can, by the way, do it without recursion even, but doing it with two nested loops looks kind of ugly, so it doesn't really do any real good. But yeah, don't have to even use recursion here. And we could use like loops, nested loops, 2 of them. Okay, so what else? Well, I guess that's that for today. So if you have any questions, let's go and see your questions, because I know it's kind of a lot to take in, I guess. All right, so if no questions, if there are this approach for parsing with a parameter showing precedence is close to what prod parsers do. Just a sec. I'm not entirely sure. Let me check. Yes, the question is, will we share the entire video? Yes, we will. Yes, I guess this is close to what kind of prod parsers do. I never wrote one, so, but I think, yeah, looks kind of close. Um, for videos, we share all of them after recording because it's all is recorded. And I think I will also share this project which I have here going. So you can kind of take it and play with it. Just waiting if you have. I'll be waiting for a couple more minutes for questions if you have them. Yeah, I'm looking at parsers. Yeah, they also right define precision. Why am I saying precision instead of precedence all the time? Yeah. They define also precedence, yes, and kind of avoid doing this duplicated code. Mm-hmm. Hmm. By the way, I found an article on prod parsers by uh, see by Nine Nystrom. Okay, yeah. Yes, prod parsers look like exactly what, well, not exactly, but close to what's going on there with precedence. Okay, so I guess that's that for today. We'll notify you on the next one. Next time we are going to create an AST, which is going to be kind of boring because a bunch of classes, you know. And I'm going to show you how the builder works and to build the AST. And I will show you how this AST printer is created. We will touch on the visitor and its internal kind of structure and how it's built. And so I guess goodbye today.